Assalamualaikum warahmatullahi wabarakatuh. Today we are going to talk or discuss one paper about with title Corrosion Behavior of 316 Stainless Steel Arc Parts in Liquid Lead at 650 degrees C under high oxygen concentration in 2022 by Ruizong Wang. Introduction. Lead is a candidate coolant for generation 4 reactor due to its favorable thermal and physical and chemical properties. Lead has advantages such as low vapor pressure, natural gamma shielding, retention of fission products, and enabling natural circulation during power outages. However, lead becomes highly corrosive at elevated temperature, posing a challenge for its use in advanced nuclear reactors. The current operating temperature lead-cooled fast reactor is limited to 550 degrees C to avoid excessive corrosion. Operating temperatures beyond 600 degrees C can improve thermal efficiency but significantly increase the corrosivity of liquid lead on structural materials due to higher solubility of their constituents. Corrosion in liquid lead includes both oxidation and dissolution. So there are two main corrosion includes oxidation and dissolution, with dissolution corrosion being particularly dangerous for alloying elements like nickel, mangan, and chromium, and also iron. Dissolution corrosion leads to degradation of surface morphology, microstructure, and material composition, which affects mechanical properties and reactor safety, of course. As for mitigation corrosion, controlled oxidative passivation can be achieved by maintaining specific oxygen concentration in the liquid lead to form the protective oxide layer on the structural material. At low oxygen concentration, so there are several options. For example, at low oxygen concentration below 10 to minus 7 weight% in lead at 500 degrees C, dissolution corrosion dominates as no effective oxide layer forms. At higher oxygen concentration, above 10 to minus 6, oxide film form on the steel surface, slowing down dissolution and reducing the corrosion rate. The formation and stability of the oxide layer depend on oxygen concentration, temperature, and the type of liquid metal and structural material. In lead bismuth eutectic, martensitic steel forms protective oxide layer at certain oxygen levels and temperatures, 10 to minus 6. At temperatures beyond 600 degrees C, the formation of stability of the oxide layer depend on oxygen concentration, as we mentioned before. In lead bismuth eutectic, martensitic steel forms protective oxide layer at certain oxygen level and temperatures. For example, 10 to minus 6 weight% at 550 degrees C. At temperatures beyond 600, the behavior of corrosion and oxide formation differs, with studies showing oxide layer formation at 700 degrees C but delamination at 800 degrees C in LBE. Lead exhibit lower oxygen activity, pure lead, and solubility in comparison to LBE, affecting its corrosion behavior under different oxygen concentration. Limited studies have explored the corrosion mechanism of pure lead at temperatures higher than 600 degrees C, with complex oxide layers formed on chromium steel alloys under various oxygen content. So the objective of this study is to investigate the corrosion behavior of 316 stainless steel in molten lead at temperatures above 650 degrees C under different oxygen concentration up to 10 to minus 2 weight%. As for the methodology, materials being used is austenitic stainless steel 316, and they have the pre-oxidation conducted in air at 400 degrees C for 24 hours. Oxide layer, formation of a protective oxide layer to prevent direct contact with PB. These are the chemical composition, and this is the impurity, the content of impurity in lead. So there is 5% bismuth, and so on and so on. ppm, sorry. So exposure to lead, it's supposed to be lead, sorry. Experimental setup, static. They use statics pre-oxidized 316 samples to lead at 400 degrees C, and the duration of exposure varied to study the effect of time on corrosion. As for the analysis, cross-sectional analysis of samples post-exposure using SEM and EDX, and these are the schematic cutting of the materials. So it's like ring and then divided into 4. These are the flow diagram of the corrosion test. So we have the electrochemical monitoring. So this is inside the glove box. There is an aluminum crucible, and it's in about 10 to minus 2 weight%. So it's they have lead inside and 316 stainless steel, and then put into the furnace with argon gas being injected with alumina rod and alumina piece. Okay, so the second case, B case, it's 10 to minus 5 weight%. So argon gas with hydrogen is injected. So in that case, it decreases the content of oxygen, and then it is welded, and that crucible with the steel and with the crucible is put into the furnace and being heat. As for the analysis, mass measurement, electronic balance being used. As for the morphology and elemental analysis, SEM and EDS was used. Cross-sectional analysis, APMA, microstructural analysis, XRD, and ion concentration, ICP-OS. As for the result, microstructural analysis, initial microstructure, the description of the microstructural 316, SS316, and it shows here, as we can see, as for the here figure 3, the weight change of 316 immersed in liquid lead at 650 degrees C. So for 1,100 hours under different oxygen concentration. As we can see, the weight changed different. At 10 to minus 2, what we can observe is the increase of the weight, while at 10 to minus 5, decrease of the weight. It means that probably we have a oxide layer formation, or and as for 10 to minus 5, yeah, we have a decrease in weight change. Okay, so this is the SEM result. So you can see here, this is the SEM. We have the original, we have the B materials, we have the A and B materials. A with several, this is the surface, surface analysis. So we have P1, P2, P3 being observed, as we can see, and also B, E1, E2, and E3. You can see P1, there are something like dimple, and we can observe a sort of formation of oxide. Or P2, and this is the P3 with this kind of surface. However, for E1, we have to magnify it more, up to 20 micrometers, in order to see the structure of the surface. This is the E2 and this is the E3. This is the surface elemental distribution. As we can see, we have the oxide. This is for material A here. You can see oxygen, PB also there. Same with the, but less of chromium. However, for B, we can see more chromium there. As for the oxide layer analysis, these are yes, we have the A material for in the condition of 10 to minus 2 weight percent, and B 10 to minus 5. You can see here that this is for the A materials. We have the iron content here, and we can see that it seems there is a formation of oxide layer. As we can see the red color here, the oxygen is oxide layer is formed in the surface. However, for the 10 to minus 5 weight percent, we can see chromium dissolve, and nickel also, and also oxygen there. This is the APMA image analysis in lead for 100 hours at 650 degrees C in the 10 to minus 5 weight percent. As we can see here, oxygen, chromium dissolve, nickel also, and iron same. And we can see ingression of PB on the surface. As for the XRD patterns of the 360 stainless steel alloy before and after corrosion in liquid lead, we can see the original. We have the Fa, chromium, Cr, and E. However, after for 10 to minus 2, we can see the formation of magnetite on the surface. However, for material B, 10 to minus 5, we can see the Fa, Cr, and E, and also PB oxide formation. And we cannot observe the formation of oxide layer or magnetite. As for the discussion, first, the corrosion in structural materials immersed in liquid heavy metals can be classified in 4 types: oxidation corrosion, dissolution corrosion, rinse corrosion, or wear corrosion. These corrosion types can act independently or in combination on the materials. This study focuses on oxidation and dissolution corrosion due to the static corrosion test method used. The corrosion behavior of 316 stainless steel in liquid metal varies significantly depending on the oxygen concentration. The key factor influencing this difference is the competition between oxidation and dissolution corrosion. Under high oxygen content, oxidation corrosion dominates the process. As for discussion 2, the surface of 316 was rapidly oxidized, forming multi-oxide layer, magnetite and FHCr oxide layer under an oxygen concentration of 10 to minus 2. The dense spinel oxide layer protected the internal matrix from PB corrosion by slowing down the diffusion of oxygen. This aligns with previous research showing that FACR spinel is effective in preventing LBE penetration and inhibiting the dissolution of alloying element. The oxygen 10 to minus 2 is considered the upper oxygen limit for liquid lead at 650 degrees C. With sufficient oxygen, continuous oxidation occurred, leading to 17.53 micrometers thick oxide layer within 100 hours, which inhibited dissolution corrosion. As a result, no nickel or chromium was detected in the liquid lead despite their high solubility in PB, especially nickel. In comparison with Seung-Gi Lee's study, which produced 20 micrometer thick B-phase oxide layer after 1000 hours at 600 degrees C with an oxygen of 10 to minus 5 weight%. The oxide layer in this study formed more quickly due to higher oxygen concentration. Discussion 3. Oxidation corrosion in alloys involves the formation of iron chromium spinel oxide layer at the interface between the liquid metal and the base metal. Over time, iron from the alloy diffuses to the oxide layer, supporting the growth of an outer magnetite layer and creating nano-level vacancies. This results in a double layer oxide structure, which lead can penetrate the magnetite layer and dissolve oxygen in the lead diffuses to the iron chromium spinel layer. Continuous diffusion of iron outward causes the outer magnetite layer to grow along the lead interface. With prolonged corrosion, tensile stress accumulates between the magnetite and ferro or iron chromium spinel layers. If the stress becomes too large, the magnetite layer may detach or eliminate it, re-exposing the chromium oxide layer to the lead, restarting the oxidation corrosion process. As for the discussion 4, we can see this is the mechanism 10 to minus 2 over here with the formation of magnetite and iron chromium spinel with chromium diffuse through the grain boundary. However, for 10 to minus 5 weight%, we can see the dissolution of chemical content. At N10 to minus 5 weight%, dissolution corrosion dominated, leading to weight loss 22 times greater than the weight gain seen at 10 to minus 2 weight oxygen. No protective oxidation layer was formed, resulting in corrosion depth of 50 micrometers and corrosion rate of 0.5 micrometer per hour in the lead. Post-corrosion analyses show high concentration nickel and iron in the liquid lead, with nickel dissolving quickly due to its high solubility in lead. Iron oxides that initially formed dissociated over time as oxygen level dropped, leading to rapid dissolution of alloy elements. Nickel dissolution was key to lead infiltration into the material, aligning with similar results from other studies. Due to low oxygen levels, dissolved iron deposited in the corrosion area, while nickel and chromium diffused to the lead interface and partially dissolved. Dissolution corrosion causes more damage to the material, highlighting the importance of controlling oxygen concentration in lead to prevent heavy dissolution and oxidation while maintaining a protective oxide layer. Conclusion, key findings: pre-oxidation at 400 degrees C improves the corrosion resistance of SS316 in static PB. The protective oxide layer is essential for mitigating corrosion. Long-term stability of the oxide layer is critical for effective corrosion protection. Future work, further research needed on optimizing pre-oxidation condition, investigation of other materials and environments to broaden the applicability of the findings. Thank you.